All right, so in this video, I want to kind of go over solubility a little bit more and look at some factors that affect solubility. So for instance, right, how like temperature and pressure play a role in like how soluble a substance may be in a solution beyond just like the basic like intermolecular forces and all of those things at play, right? I really want us to focus on like more of the environmental factors that could tune solubility for a solution. The solubility is, to be a little bit more clear, like the maximum concentration that a solute may have in a solution or in a solvent. And when it does reach that maximum concentration, we say that the solution is saturated, right? It's kind of like it's at its most concentrated point. And if we were to maybe add any more solute to the solution, it wouldn't dissolve, right? So every solution has kind of like that maximum critical point to it. Even table salt, which you think is very soluble in water, does have a limit. So right when we first introduced solubility in an earlier video, right, we said like 39 grams of sodium chloride could be dissolved into 100 milliliters of water. That's to say that if I were to try to add 40 grams of sodium chloride, it wouldn't dissolve, right? I would get some saturated solution and some excess solute still just kind of like sitting there in the solution. Now, when that happens, right, we can kind of picture that close up, like we see right here, right? The sodium chloride maybe has mostly dissolved, but there may still be some solid bits in there. And oftentimes we want to kind of think about that as like a static point, like, okay, well, now the solution's just kind of like stuck, right? It's not going to do any more of this dissolution reaction. But in truth, right, there is still like some of the solid being dissolved. At the same time, there's still some of that like aqueous solute that is then going back into the solid state. And so this is just another example of like chemical equilibrium, which we brought up before when learning about like vapor pressure and kind of how a gas can be in equilibrium with its liquid phase. Right here we have basically an equilibrium of a solute with its solution phase. And so, right, you're going to see this again pop up in Chem 163. So I figured I'd give you like a little preview of it right here. But right, really what we want to note here is that once that solution has kind of reached that equilibrium point and the solid is dissolving while it's also being reformed at the same rate, right, that is when you have a saturated solution. Now, as mentioned before, right, solubility is going to differ with temperature. For instance, a lot of ionic compounds will have higher solubility at higher temperatures. And that can really be tied back to the Gibbs free energy, right, and how ionic compounds tend to have a positive delta S when they dissolve into solution. And so having a higher temperature then lends itself to having a more negative Gibbs free energy, or delta G. And if you look at the figure to the right here, right, you can see some of the solubilities of different ionic compounds at different temperatures. And for the most part, right, we see kind of a positive correlation there, that at higher temperatures, you have higher solubility. We can actually like kind of take advantage of that fact and make a solution that sort of breaks the rules of solubility. So for instance, right, let's say I have a solution of potassium chloride, which is in this purple line here. And maybe I make a saturated solution of potassium chloride at 70 degrees Celsius. So right around here, right, maybe about 50 grams of KCl dissolved into 100 grams of water. I could then lower the temperature very gently. So, right, just kind of going to maybe 20 degrees C on this curve right here. And right at 20 degrees C, the solubility of KCl is only 30 grams per 100 grams of water. But if I've done everything super carefully, I still have 50 grams of potassium chloride in the solution because I was able to dissolve all of that at that higher temperature. I've now just very carefully cooled down the solution to kind of be higher than what the solubility would suggest. This resulting solution is called a supersaturated solution. It's like beyond the saturation point. And so, right, with the supersaturated solution, it can show some really cool behaviors. So for instance, if I have like a supersaturated solution, like the KCl described before, any disturbance to it will kind of make it realize like, oh shoot, I have way more solute dissolved than I should. And so what that will do is then cause the solution to suddenly recrystallize, right, and produce the solid once more. So that's shown right here in this first figure, right where I have just like a supersaturated solution. It looks all fine and homogeneous and everything. There's no problems in it, but dropped into it is just one little seed crystal. And that kind of reminds all of the solute that's in that solution to get in line and start making all of these crystals as a result. Eventually, the solution will reach that normal saturation point, right? Once it has undissolved a bunch of the solute, and so I think that that's just kind of like a really cool feature of supersaturated solutions. I actually have some like chemical hot pack that I'll probably bring into class when I next see you, and you can see like a supersaturated solution turning into basically a solid just right before your eyes. It's really fascinating and really interesting to see. So for other types of solutions, we actually see a different relationship between temperature and solubility. And to kind of understand this, right, I want us to consider like a gas being dissolved in water. So, right, gases can dissolve in water. For instance, oxygen dissolved in water is like super important for fish being able to breathe as they do through their gills, right? There's dissolved oxygen in the water that they swim in, and that oxygen is then used by them in the same way that we just breathe oxygen through the air. But so, right, when a gas dissolves into water, it's actually losing entropy as it does that, right? Because a gas is like super high entropy. It's very random, it's all over the place. But once it goes into solution, even though that solution is like kind of mixed up and a little bit random, compared to the gas, a solution is not as highly entropic as the pure gas was. So what we traditionally see is that in a gas dissolution reaction, delta S is going to be negative because you're losing that randomness. You're kind of becoming more ordered. And what that means then in terms of the Gibbs free energy of the reaction, the delta G, right, you're going to see at higher temperatures delta G is going to become more positive because delta S is also negative. And that's not really good for making the reaction happen, right? A reaction is spontaneous if delta G is a negative value, but if delta G ends up being a positive number, then that process just like isn't going to happen. So what that basically means is that at higher temperatures, you're going to see lower solubility for gases. So right, similarly here, I have a few different gases shown and their solubility in water at different temperatures. And right, what we notice is that like all of these are kind of dropping as the temperature increases. I think we're already actually pretty familiar with this subject. If you've ever had like a warm soda, right, the bubbles in it are like less bubbly, and that's because the CO2 that was dissolved into the soda is much less dissolved at a higher temperature. That's why like it's really nice to have that like ice cold, McDonald's Sprite that like burns so good. That's because, right, at lower temperatures, you're gonna have more CO2 dissolved or just more gases dissolved in general. And right, that's really true for like any gas. Kind of related to this in terms of just like how soluble a gas is. Temperature isn't like the only thing that affects gas solubility. Pressure will also play an important role. And I think that we can like pretty easily understand this as like literally at higher pressures, it's like you're sort of forcing the gas molecules to go into the solution, right? So at higher pressures, you're probably going to see higher solubility of the gas, right? So that's kind of illustrated here with these different containers, right? On the left, there's a lower pressure container where there are less gas molecules dissolved. And then in the middle and on the right, there is higher pressure being applied to the gas. So it's kind of pushing the molecules just into the solution. And so you're going to have a higher solubility there. Beyond that, though, there is sort of like a mathematical correlation between pressure and solubility, and that's represented in Henry's law, which says that the solubility of a gas, which we'll just call capital S, is directly proportional to the partial pressure of the gas, so P for pressure, and right, that can just be summarized in this equation here, Henry's law. Now the other kind of variable in this, Kh, is referred to as the Henry's law constant. It is not like a universal constant. It's meant for specific gas solvent combinations and at specific temperatures too. So this is just like kind of a constant that you may find in like a reference book or in your text or whatever. So right, for three different gases shown on the graph here, we can see three different Henry's law constants associated with them. As far as I kind of understand, there's no like trends for the Henry's law constant. Like I can't just look at a chemical and be like, oh, that's going to have a high KH value to it. But right, it is just kind of like a experimentally found constant for that specific solution mixture. But so this is really just to, again, give us like a more full picture of solubility and kind of like why solutions form, right? It's a whole mix of factors, things like the intermolecular forces between all of your different parts of the solution, things like just the environment, right? The temperature and the pressure around the solution can also play a role as well. But so please let me know if you have any questions, and I'm happy to help. Bye.